Now let's talk about rational exponents with negative numerators. So you might recall from working with exponents before that if I had like a to the negative r, that became 1 over a to the r, right? Negative exponents were fractions. If I had 3 to the negative 2, that became 1 over 3 squared, which was 1/9, right? Well, now we're going to have to do the same thing. So if I have a to the negative m over n, this means I need to move it to the denominator. So let's look at this first example. I have 16 to the negative 3/4. That gives me 1 over 16 to the 3/4. I then need to go ahead and solve this like we did at the tail end of the last video by pulling this apart. So I have 1 over 16 to the 1/4 cubed, which is I have 1 over 2 cubed, which is 1/8. For this second example, I'm going to have 1 over 25, 3 to the 3/2. That's 1 over 25 to the 1/2 cubed. So I get 1 over 5 cubed, which is 1 over 125. I'm going to go ahead and clear room because problem 3 takes a little bit of space. So let's say I have 8 over 27 to the negative 2/3. That gives me 1 over 8 over 27 to the 2/3. Well, darn it, this is a complex fraction, right? Let me go ahead and distribute my 2/3 to my 8 and my 27. This is a complex fraction. For a complex fraction, I need to keep in mind that this right here means division. So I have 1 divided by 8 to the 2/3 over 27 to the 2/3. So I keep my first fraction the same. I change from division to multiplication, and I flip the second fraction. So now I have 27 to the 2/3 over 8 to the 2/3. Told you this was going to take a lot of space. Now I have to solve this. I have 27 to the 1/3 squared over 8 to the 1/3 squared. That gives me 3 squared over 2 squared, which is 9/4. For the last example here, I have an exponent. Just friendly reminder that we can put rational exponents on variables. So I have 1 over r to the 2/3, and I can't simplify that any further. So what are our rules for rational exponents? Well, guess what? They are the same as for all real numbers, especially for our whole numbers that we were working with before and the integers, right? We only had negative and positive whole numbered exponents. So for example, the product rule, if a is any real number and r and s are integers, when I multiply them and they have the same base, I add them. So here if I have 2 to the 1/2 times 2 to the 3/2, that becomes 2 to the 1/2 plus 3/2, which becomes 2 to the 4/2, which is just 2 squared. If I have 2 to the 1/2 times 2 to the 1/4, I take 1/2 plus 1/4, but wait, I can't add those. I need to write 1/2 as 2/4. So I would get 2 to the 3/4. Not too shabby. The negative exponent rule we already kind of talked about a little bit about, right? So if I have 5 to the negative 1/3, that becomes 1 over 5 to the 1/3. If I have x to the negative 3/4, that becomes 1 over x to the 3/4, right? It's a negative exponent. You push it to the denominator. Also keep in mind our quotient rule. If a is a real number and r and s are my integer exponents, I subtract them, right? If I had 5 squared over, well, let's do 5 to the 12th over 5 cubed, that becomes 5 to the 12 minus 3, which is 5 to the 9th, right? So now if I have 5 to the 2/3 over 5 to the 7/3, I take 5 to the 2/3 minus 7/3. That gives me 5 to the negative 5/3, which becomes 1 over 5 to the 5 thirds. And we can't simplify that any further as much as we want to because it's not the prettiest looking answer. Also, keep in mind the power rule. The power rule distributes across exponents. So if I have a to the r power raised to the s power, I multiply those powers, right? So if we have a power raised to another power, we multiply. So I would get, for this first example, 3 to the 4th, x to the 1/2 times 4, which is x to the 4/2, y to the 2/3 times 4, which is y to the 8/3. Oof. So I have 3 to the 4th x squared, because this can simplify. Remember to always simplify your fractions. Y to the 8 cubed. Here, I'm not really so much raising an exponent to another power, but I am multiplying a binomial by a monomial. That'd give me m to the 15/4 minus m to the 3/4 times 1/4. Oh, wow. 15/16. Let me start over. We have to multiply these fractions. When you multiply fractions, you multiply the numerators and the denominators. So if I have m to the 3/4 times m to the 5/4, I get m to the 15/16, to the 15/16, because 3 times 5 is 15, and 4 times 4 is 16. Now, if I have m to the 3/4 times m to the 1/4, that gives me m to the 3/16. So this is my final answer. And I cannot simplify this any further because my exponents are not to the same power, right? We can't combine like terms unless our variables are raised to the same power. So how do I know when an exponential expression is fully simplified? Well, it's the same as when we were working with integer exponents. Each base occurs only once. There are no parentheses. No powers are raised to other powers, and there are no negative or zero exponents. So let's solve a pretty gnarly looking exponent. 5x to the 4th over y to the negative 6th over x to the negative 2, y to the 1/3. So what we want to keep in mind is PEMDAS. What does that mean? That means we want to take care of what's inside our parentheses first, and that means we should definitely simplify our inside our parentheses before we distribute this negative 2/3. So if I have x to the 4th over x to the negative 2, that's x to the 4 minus negative 2. And then I have y to the negative 6 minus 1/3. I'm going to rewrite 6 into thirds. That'd be 18 thirds. Yes. All to the negative 2/3. So I have x to the 6th, y to the negative 19 thirds, all to the negative 2/3. So now I have x to the 6th over y to the 19 thirds, all to the negative 2/3. And I'm going to go up here to distribute that. So I have x to the 6th over y to the 19 thirds to the negative 2/3. I have to distribute that, remembering that I just multiply it in. So I have 6 times negative 2/3, which gives me x to the negative 12 thirds. I have negative 2/3 times y to the 19 thirds, so I get y to the negative 38 ninths. These are both negative, so they have to change places. I've got y to the 38 ninths over, well, 12 divided by 3, that's going to be 4, x to the 4th. Now this is our final answer, and I know it doesn't look amazing, but it is correct.